This week's lesson is on hypothesis testing for mean. The hypotheses are still going to be statements about parameters, except now instead of the parameter being the population proportion, the parameter is going to be the population mean. Recall that X bar represents the sample mean, and then this kind of strange swoopy letter M, mu, represents the population mean. The mu with a little 0 next to it, that's actually going to be a number in the problem, so it'll be like 5 feet 10 inches if we're talking about height, or maybe 23 if we're talking about ACT scores. And the little shaded area in the tails represents the p-value. If the p-value is less than the level of significance, then you're going to reject the null hypothesis, and then when you write the conclusion, you are going to have evidence. The symbol that we use for the level of significance is alpha, and it's usually 5%, and that makes sense to put 5% in the tails of the normal distribution. This is just kind of consistent with our level 2 on the empirical rule. And just as before, the technical conclusion needs to be in a very specific form and contain very specific pieces of information because this is a scientific statement. You either have or don't have significant evidence. It's going to be the 5% level, or if they give you a different number in the problem, then it'll be at the 1% level. And then just like in court, conclusions are always about a person's guilt. You are either guilty or not guilty, and that corresponds to the alternative hypothesis. Conclusions in hypothesis testing are always about the alternative hypothesis. So my wife is always nervous about being a bad mom, and so she wants to limit the amount of screen time that our kids get in a day. And so I assumed that the distribution of video watching is normally distributed. That's reasonable. Sometimes the kids watch a little bit more, sometimes they watch a little bit less. And then so based on this data, we're gonna test the hypothesis. She hypothesizes that we're bad parents, and let's see how it comes out. Okay, I don't have the patience to write down 10 numbers, but I sampled 5 random days. So the null hypothesis goes to the idea that we watch 4 hours of videos per day, and the alternative hypothesis is that we watch more than 4 hours of videos per day. This is my drawing of a calculator. There's buttons on it, right? The 2 calculator operations that we're going to use are t-test and 2samp t-test. Since there's just one population in this problem, we're going to use t-test. There's 2 choices for the input. It can either be set on data or stats. In this problem, we were given the raw data. So the first step is to edit the list and put the data in the calculator. And then I'm going to leave my t-test set on data. The null hypothesis is 4 hours of video watching. And we are testing the hypothesis that we're bad parents, which corresponds to letting your kids watch more than 4 hours of videos per day. All right, I've got to come back and fix this. Like I'm supposed to be the teacher, and I forgot this little stupid thing. We're not using the normal distribution anymore because of the whole SX versus sigma issue. So these aren't z-scores, these are t-scores. So we got a t-score of 0.6. Remember, these t-scores are on the same level as the empirical rule, so plus or minus 2 or more is kind of starting to be an extreme t-score. So our t-score of 0.6 is not extreme at all. It's very small. It's inside level 1. The p-value was 0.2903. This represents a probability. 30% chance is it's not small. I'm not comfortable with that level of risk. So we need to ask ourselves, is 0.29 less than 0.05? No. So we did not get an extreme t-score, and we did not get a small p-value, so we're not going to reject the null hypothesis. We do not have evidence. Let's look at the reason that we don't have evidence in this case. The main issue is the very small sample size. This only comes from a sample of 5 days. In fact, when you look at the sample average, we got 4.34. So our data does support the idea that I'm a bad parent, but I just didn't collect enough data for this to really be significant evidence. We do not have significant evidence at the 5% level to conclude that the average video watching per day is larger than 4 hours. So sorry, honey, it looks like we're good parents. I guess that's just, I mean, you can't argue with science. There's a relationship between finding confidence intervals and rejecting or accepting the null hypothesis in a two-sided hypothesis test. Both of these processes involve finding this standard error in the distribution of the samples and then going out to level 2 on the empirical rule. Both objects involve the middle 95% of the distribution of samples, and confidence intervals are supposed to be a range of plausible values. So the conclusion is, if you build a confidence interval and the number from the null hypothesis is inside the confidence interval, then that means that mu0 is plausible, and so we are not going to reject the null hypothesis. However, if you build a confidence interval and the number in the null hypothesis is outside of the confidence interval, that means that it's not plausible, and so we are going to reject the null hypothesis. So these two processes are equivalent. They have a different context, but the math behind them is the same, so you can actually always use a confidence interval to tell you whether or not you're going to reject the null hypothesis. He needs bigger glasses. Big glasses on this guy. This guy's supposed to be shrugging his shoulders. Does it look like he's shrugging his shoulders? I don't know. It looks weird. I'm bracing it. The accompanying data table shows reaction distances in centimeters for the dominant hand of a random sample of 40 independently chosen college students. Smaller distances indicate quicker reactions. Okay, here's the problem on StatCrunch. I'm just going to have a look at one of these histograms so I can get a sense for how I'm going to make it. So it looks like the bins all start at 0, 1, 2, 3, 4, and it looks like they the bin width is 4. I'm going to open the data in StatCrunch. I'm going to make a histogram. I'm going to select the column 1, and then my bin started at 0 and the bin width was 4. So I get this kind of graph right here. Let's see if that matches any of these. B. Sweet. Oh man. Okay, this distribution is it looks like a turtle to me, and the tail is on the right side. So this distribution is slightly skewed to the right. Okay, now it wants me to make a confidence interval, a 95% confidence interval. Let's do that. So I'm going to use t-stats since this is a problem about the mean. There's just one sample in this problem. I have the data. The data is variable 1. And we have two choices here. We can do a hypothesis test or a confidence interval. We want a confidence interval and said the C level was 95%. It gives me this upper limit and lower limit. So how many decimal places? Round to 2 decimal places. So I will keep 3. 7.926 will round to 7.93. 10.873 will round to 10.87. Fantastic. Okay, let's talk about this interpretation of confidence intervals. This picture represents the distribution of all of the samples, and what we're trying to figure out is where this thing, the true population mean, where should that go? So if we get a very common sample, then we would put the sample mean in the middle, and maybe because this was a common sample, the true population mean might be somewhere like right here. Or maybe it's over here. But if for some reason we get a very strange sample mean, then maybe the population mean, the true value of the population mean, is going to be out in one of the tails because we got a kind of extreme sample. Another way to interpret a confidence interval is kind of a way of saying how good a job does random sampling do. So this process of repeating the sample many, many times, if you construct a 95% confidence interval, then you're going to expect that this job of collecting a random sample did its job 95% of the time. Then there's going to be some fluke chance, some 5% of samples that are going to produce a confidence interval that does not contain the true population mean. Killing it. Nice work. Thanks, StatCrunch. I really need a boost of confidence right now. Oh man, hypothesis test 2. This problem is a nightmare. Why did I do this? Suppose the professor said the population mean should be 10 centimeters. Test the hypothesis that the population mean is not 10 centimeters. So this is a two-tailed alternative hypothesis. So the null hypothesis, I'm going to give the benefit of the doubt to what the professor said. And then the alternative hypothesis is that it is not equal to 10 centimeters. So I chose equal and not equal to. Okay, back to StatCrunch to get the test statistic, and I'm sure they're going to ask me for the p-value again. So going through the same setup to do a t-statistics with one sample, except this time instead of choosing confidence interval, I'm going to pick hypothesis test. Mu was equal to 10, mu was not equal to 10. You see you have the three choices here. We're going to choose not equal to. I did not get an extreme t-stat here. This is inside level 1. Round to 2 decimal places, negative 0.0823, so it'll just be good job. P-value, I knew it, 4151, so I just keep it. Good job. This is not a small p-value. The p-value is greater than the level of significance. So we do not reject the null hypothesis. Your problem may be different than this, by the way. This is just, I don't know how the computer cooks up these numbers. So your answers may totally be different than this. This corresponds to having insufficient evidence. Good job. Please be the last part. Yay. When you're sampling for 2 population means, there's 2 different ways to do that. One of them is called dependent samples, and one of them is called independent samples. Sometimes there's a natural way to pair the data points from 2 different samples together. And if you can do this, you should, because in general, dependent sampling is a stronger kind of statistics than independent sampling. For example, suppose that you were asking the question, do husbands and wives spend similar amounts on their car? I'm going to choose the first population to be the husbands and the second population to be the wives. And there is a natural way to pair. I mean, if we're trying to compare the amounts that husbands and wives spend on their cars, then you need to pair the husbands and the wives together. This is to your advantage in statistics, because actually this is a way of turning 2 variables into 1 variable. Now, instead of studying the value of the husband's car and the value of the wife's car, you can just study the difference between the price of the husband's car and the wife's car. It's kind of a nice trick to turn 2 populations into 1 population. Another common example of dependent sampling is if you're doing a before and after study. You know, if we were studying, say, for example, cholesterol medication, then instead of just studying some people's cholesterol that didn't take the drug and some people's cholesterol that did take the drug, measure somebody's cholesterol level and then start them on the medication and then measure their cholesterol level again after. This will just result in stronger statistical practice, and it will be easier for us to have evidence. If the medicine is really working, it will be easier for us to have evidence, and the width of confidence intervals will be more narrow. Anything that is not dependent sampling is independent sampling. For example, suppose that we were studying the weight of athletes in different sports. I chose baseball and soccer. Well, the book chose baseball and soccer, and then I copied their example. And I'm going to let x sub b equal baseball and x sub s equal soccer. So we're testing if there's a difference. So both of these groups are just male athletes without any evidence. I would have no reason to believe that one group was heavier than the other group. So the null hypothesis is that the population average weight of baseball players is the same as the population average weight of soccer players. And then since we're testing if there is a difference between the two populations, this is going to be a two-tailed alternative hypothesis. Back in StatCrunch, I'm going to open the data. And then I'm going to select two samples in my t-statistics. Observe that paired data is a choice, but in this problem, it's just some soccer players and some baseball players, and so I don't really have a way to naturally pair them together. Just as a quick note, you might see pooled variances. That's beyond the scope of this class, so I'm just going to tell you we're not going to pool the variances. In Stats 1, this isn't something that you ever do. Sometimes people do a little bit of algebra, and instead of writing mu1 equals mu2, they'll write mu1 minus mu2 equals 0, just like we saw with proportion confidence intervals and proportion hypothesis testing. Anything that's about two populations, what we're really concerned with is there a difference between the populations. So that's why the 0 is always in there. Okay, and we have very strong evidence. It looks like this is a huge t-stat. We're almost at level 5, and the p-value here, they give me less than 0.0001. Yeah, look at some of these soccer players, only 158, and here's somebody in baseball at 222. I just want to make sure that everyone understands that our interpretations are about population means. We're not really making a statement about a single individual baseball player or a single individual soccer player. We're making a statement about the average of all baseball players and the average of all soccer players. So it's still possible to have a baseball player and a soccer player that are similar in weight. Suppose we're studying the price of buying textbooks at two different universities, then I can make this data matched pairs by ensuring that the textbooks are from the same course. So I compare a college algebra book to a college algebra book, and a statistics book to a statistics book, and like a chemistry 1 book to a chemistry 1 book, just from the different schools. So the actual variable in this problem is the difference in price. I made a choice to do a book from University A and then the matching book from the same course in University B, and I'm going to subtract their price. Since I don't know anything else about these two universities, the null hypothesis is going to be that there's no difference. Without any evidence, there's no reason for me to believe that books at University A will be more expensive or less expensive than books at University B. So we use mu with a little d next to it to represent the average difference. So we're going to test if there is a difference. What it would mean if there is a difference in prices is that the average difference is not equal to 0. I'm going to open the data in StatCrunch. Since I'm comparing apples to apples here, the books from the same courses in the two different universities, I'm going to choose paired data. I chose sample 1 to be University A and sample 2 to be University B. You have 3 choices for the alternative hypothesis, and we're going to choose the two-tailed version since we're testing if there is a difference. And in the problem the computer generated for me, I ended up with a relatively extreme t-stat here. I am outside level 3, and you can see I got a very small p-value. The p-value is less than the level of significance, so we are going to reject the null hypothesis, and we do have evidence. So we do have significant evidence at the 5% level that the population mean difference in price is not 0, which means that there is a difference in the average price of these textbooks. This is a bit subtle, but I want you to think about the two statements. The difference between the average and the average of the differences. They're not the same thing. They mean something different. In one of them, you calculate the two averages and then you subtract. And in the other one, you subtract and then you calculate the average. In matched pairs, like the problem about the textbooks, we are making statements about the average and the differences. And in the example on the other page about soccer and baseball, we're making a statement about the difference between the averages. It's okay if the subtle distinction between the difference of the averages and the average of the difference doesn't sink in right away. Sometimes it just takes a little bit of that rolling around in your head for the concept to really click. For now, just hop into my math lab and try the homework, and please reach out to me if you have any questions.